Thank you. So we are continuing with our discussions on the bipolar IC fabrication. I have mentioned the steps involved in the fabrication, and now I am showing you the illustration of the chip cross-section after the fabrication is over. Okay? This is the chip I want to realize. Is a very simple. This cannot be called a chip. It's really a small scale integrated circuit containing one transistor and one resistor. Simplest example, just like proton, hydrogen atom, just like that, electron and proton, is the simplest example of a chip having one transistor and one resistor, electrically isolated. So I have shown that here. You see that. Only there is a little confusion in this diagram that here this blue region is N plus emitter, whereas this is also N plus. Please remember I have not blue because of the my problem in drawing. I have drawn it like this, and this region is P base, P-type base. This region is P-type base. From here to here, this region, this N-type epitaxial film, this is N-type epitaxial film, from here to here, as well as from here to here. These are islands, which I have told you in the last class. This particular island, N island, contains the BJT, the transistor. Whereas this particular island contains the resistor R. This is the R, and this is the BJT. Okay? If you compare the different fabrication steps which were discussed in the earlier class, you will find that these are all implemented one after another in getting this end product, which is the cross-section of the chip at the end of the fabrication. You see that I had carried out the buried layer formation, and these are the buried layers now. This buried layer is the collector for this transistor, whereas this buried layer is optional, but it serves some purpose. We're not going to discuss that. This also serves some purpose. Within this N-type collector and this N-type island, there are isolation regions surrounding, which electrically isolate the different tops or wells. In this particular well, N-type region, we have developed the BJT by successively doing the different diffusion steps. For example, we have carried on the base diffusion, P-type base diffusion, the P-type base diffusion, and the P-type diffusion for the resistor formation simultaneously. Therefore, these two diffusion normally are called BNR diffusion. In the language of technology, this particular diffusion step, which is used for the formation of the base boron doped region and this boron doped region, both are P. Please remember, both are P region. This is P region and this is also P region. For the formation of these two P regions, I have used a step called BNR, B and R. BNR means actually B and base and resistor diffusion. In short called BNR diffusion, base and resistor diffusion. And after the base and resistor diffusion, I have carried on diffusions for the emitter and collector contacts simultaneously. Here you note that in the earlier case. Diffusion for the emitter and the collector contact have been done simultaneously. And ultimately, after completing all the diffusion and driving steps, we cover it by oxide, and then H windows here, 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 here. These windows are called contact holes. In this particular example, there are 1, 2, 3, 4, 5 such contact holes. Thereafter, after the contact hole formation, you please compare with the earlier steps. We metallize it. Everywhere you deposit a metal film. And using the last but one mask, we pattern the metal. The green one is a metal here. The green level is a metal. We pattern it to form the circuit, this particular layout. As I told you, this is nothing but comparable to hydrogen atom in terms of simplicity. Just one transistor and one resistor. So you see that this is nothing, this is the metallization for that particular chip. Of course, I have not shown the sidewise ones. The input and output has to be must be taken sidewise from the chip. I have shown only the cross section in a particular plane. If I had drawn the cross section in this plane, I could have shown how these input and output metal lines are flowing, which I have not shown yet. Okay? And ultimately you see that you form the chip where this is your VCC. Just compare with this. You have to apply VCC here. This terminates into a bond pad. This is the ground emitter. Again terminates into a bond pad surrounding the chip. This is the input base, terminates into a bond. We have to apply input signal there. And this is the output, the collector and one of the resistor terminal, common. This is a node. And that's the output. So it also terminates in another bond pad. So in this chip, how many bond pads are there? 1, 2, 3, 4. Again, the example of simplest IC chip, just like our hydrogen atom. Simplest IC chip with 4 bond pads, 1 for power supply, 1 for ground. You have to supply that. There is no other alternative. That is common for all chips. And then 1 for input, the other for output. Suppose I extend it to an amplifier circuit. For example, I just develop an amplifier, a 2-stage amplifier, just using a number of transistors and stages. Now, how many such bond pads should be there in an amplifier circuit? Again, perhaps the same number, but there are requirements of certain other things. For example, in op-amp is not an amplifier, you have seen, but there is some preset adjustment, 2 power supplies, negative and positive. So that's how we get higher number of bond pairs and higher number of pins in a typical op-amp. It is more than this so 4 is the simplest. You please remember, 4 bond pairs the simplest one in any IC chip. And this is the basic thing in a bipolar IC. Please remember, this is a basic thing in a bipolar IC. It can be used as a switch. It can be used as an amplifier stage. Only for amplifier stage, I have to have a better arrangement for biasing circuit, which is not there at all here. We are not bothered about the temperature stability, etc. in digital techniques. Whereas in bipolar, you have to have a constant gain, and it's direct coupled in many applications. And unless we maintain the biasing conditions properly, it will not work satisfactorily. That's the difference. A bipolar integrated circuit, a linear integrated circuit, is therefore design-wise more complicated than a digital integrated circuit. Please remember this. Regarding this resistor, so typically suppose this is 1 kilo ohm. 1 kilo ohm. This resistor is 1 kilo ohm. How to achieve that? You see that resistor is formed along with the base. And base has got a certain sheet resistance. What is that sheet resistance? You know that. What is sheet resistance? How do you define sheet resistance? So if we have a square sheet of length L and side is also L, and thickness may be some, say, W. This is length, the side is also length. L, both are L, because it is square sheet. Thickness is W. And if rho is the resistivity of this sheet, what will be the resistance for current flowing in this direction? R is equal to rho L by A. L by A means L into W. That means this is equal to rho by W. This particular quantity R, you see that is independent of L. This quantity, the resistance of a square sheet, is independent of the length dimension or width or the breadth dimension. It is dependent on resistivity and the thickness. This quantity is normally called sheet resistance of a film and is expressed in terms of ohms, which I think per square, or ohms per square. This square otherwise is not meaningful so far as dimensions are concerned. This is just meaningful to show, to differentiate it between from ordinary resistance. Ordinary resistance is ohms, unit is ohms, but because also its unit is ohms, R. Unit is ohms. It is not ohms per square centimeter, it is ohms per square. This square has got just to signify that it is sheet resistance. We use this word square. There is no other. Please remember, this is the normal, that I've seen the tendency. Many students, they write square centimeter. This is a wrong thing. This is ohms per square. This square is meaningful only to signify that it is sheet resistance and not ordinary resistance. And this is a very important thing in ICs. Whenever we quantify a film, a layer electrically, we specify its sheet resistance. For example, the base diffusion, we carry on. And at the end of the entire process, the base diffusion is characterized by a quantity is base sheet resistance. Base layer sheet resistance. What is the ultimate sheet resistance of the layer, P-type layer, which we are calling base? And usually the base sheet resistance, base sheet resistance R square for base is around, say, 200 ohm per square. Typically. You see that this base sheet resistance is typically around 200 ohms per square. It may be 500, 100, but typical design, it is 200 ohms per square. How to realize then 1 kilo ohm? I have to shape this base layer here such that the length is 5 times more than the width, so that there are 5 such squares present. 200 ohms per square means when I stack 5 squares serially, the resistance will be 1 kilo ohm. So what we do simply, we shape this particular region in such a way that its aspect ratio, the length by width is called aspect ratio, is 5. Showing it, so for the resistor, it will be something like this. So what we have done, you see that this particular base diffusion region has been shaped like this. Okay? In such a way that the length, effective length to width ratio is approximately 5. Approximately, it depends on the design. So that if the base sheet resistance is 200 ohms per square, the resistance offered by this resistor will be 1 kilo ohm. So you see that in bipolar integrated circuits where resistors cannot be unavoidable, we have to use resistor excepting for I2L logic. In all other bipolar integrated circuit, resistors are essential, and these resistors are realized using the diffuse layers normally. So what is the problem of these resistors as compared to the resistors which you are using in normal circuits? Yes? One is the distributed capacitance around it. That is there. Second is the temperature sensitivity, TCR, temperature coefficient of resistance. TCR or temperature coefficient of resistance. Temperature coefficient of resistance. Being a semiconductor, you know that electrons and holes can be generated at higher temperature. So if you raise the temperature, conductivity generally increases. And lower is the doping, more will be the temperature sensitivity of these resistors. It is found the resistors formed during base. You know that in these structures, base has got a very relatively low doping. Base has got a relatively low doping, around 10 to the 617 per centimeter cube. And as a result, the resistors realized by using the base stops or base diffuse layers, they have a fairly high value of TCR, around 1000 to 2000 ppm. 1000 to 2000 parts per million per degree centigrade. If you are interested in realizing resistors of values several hundreds of ohms, so around say 500 ohms to several kilo ohms, so maximum 10, 15, 20 kilo ohm, then it is wise to use base diffusion, because base diffusion has got such a sheet resistance, it is suitable for realizing those ranges of resistors. Suppose I want to realize 100 kilo ohm using base resistor, what will be the shape? I have to have a Mendel line shape, just like this, to extend the length. I should have a very large L by B ratio in order to achieve 100 kilo ohm, and what will be the bad effect of that? It will occupy most of the cheap area, which is so good, so important, so expensive. And therefore, you know that whenever you want to realize a very high resistance, you are in problem. When you are interested in realizing a resistance of the order of few kilo ohms, this base resistor is okay. Unfortunately, it suffers from a high TCR. Therefore, what we should do is really, we should use a ratio-based design. We should not design in such a way where the absolute value of the resistance is important. Rather, the ratio of the resistors are important. R1 by R2 is more important than the absolute value of R1 or R2. You can design analog circuits that way, where it is more important to consider the ratio of the resistors rather than the absolute values of the resistors. Why I am saying so? In that case, even if there is a drift with temperature, the ratio will not alter that much. Individual resistors may drift with temperature quite appreciably. The ratio of the resistors will not drift that much. So this is called a ratio-based design. But whenever you are interested in fabricating a high value of resistor, you are in problem. Can you tell me how can realize a high value of resistance? in a small region. No, actually a register called pinched base register. Let me show you. Pinched base register. Pinched base means between the emitter and the collector, this region is very narrow, you remember? The physical base width is very narrow. Am I correct? Between this emitter layer and the collector, this base layer is very narrow, usually of the order of micron. Otherwise, if you do not maintain that, your gain will be very less. In order to achieve a high transistor gain, the physical base width should be of the order of micron. So if I have a contact here and here, do you follow? On either side, suppose I don't use this structure as a resistor, as a transistor. I in a separate block, I make similar things, and I put a contact here and a contact here. So that what will happen? The pinched base region, this is what is called pinched base. The pinched base region, because it is extremely narrow, will provide a very high resistance. And this is what is called a pinched base resistor. Resistances of the order of hundreds of kilo ohms can be easily realized using these pinched base combination. But they again suffer from a very high TCR. A very high TCR, naturally the resistivity is very high, means TCR is also very high. But it is found in most cases in bipolar ICs, TCR is not that important for high resistors. For high values of resistors, wherever used, TCR is not that important. Similarly, in bipolar circuit, you also need resistors of the order of few tens of ohms. So 50 ohms, 100 ohms. Do you think that base diffusion should be good for that purpose? I want to make a 30 ohm resistor. Do you think the base diffusion should be used for that purpose? No. Because base shift resistance is fairly high, in excess of 200 ohms per square, maybe 200 or even more than that. So what I should do? I can use the emitter diffusion. You remember, of all the doped layer, it is the emitter and the collector contact region which are most highly doped. Emitter, you know, for achieving a very high gain of transistor, you remember that one has to achieve a very high injection efficiency of the emitter base junction. And for that, what we do? We maintain a very high emitter doping compared to base. That is a fundamental requirement of a good bipolar transistor. Because our emitter doping is very high and it is the last doping, its shift resistance is usually quite small. What is the order of emitter shift resistance? Even less than 10 ohms per square. Emitter shift resistance is of the order of 10 ohm per square. So, okay, so you can now utilize, for example, I want to realize just here, in place of if 1 kilo ohm resistor for a certain circuit, suppose I want to put a small feedback here in the emitter loop, which is necessary for our emitter, bipolar circuit, linear circuit. I put some 30 ohm here for a small feedback to control the gain. And very, very important in bipolar circuit. And 30 ohm resistance, suppose I want to implement here. So what I will do? I keep it covered till the emitter diffusion window is open. I keep this whole thing is covered by oxide till the window for emitter and collector contact diffusions are opened. Then I open, along with the collector contact and emitter diffusion, I also open the window in this region. Do you understand? Of course, before that I have to have the base, otherwise there will be problem, isolation problem in there. Initially I have a base diffusion, just like this one, but within that base diffusion, I open a window of proper shape, proper L by B ratio, so that I can realize, for example, as I told you, 10 ohms is per square, maybe the emitter shift resistance. So what I have to do? I have to open a window here whose aspect ratio, length to width ratio should be 3 only. Along with the emitter diffusion, I can open a window here whose length to width ratio should be 3. Can you tell me what will be the problem in this case? Suppose I want to realize the resistor by this technique, what could be the problem facing? I think you understood what I mean. What I said that this is my thing. Okay? This is N-type epi layer, this is P plus isolation, this is P base, and then within this we have got N plus emitter. So this is the picture of a resistor which is realized using emitter diffusion. Alright? And then I have opened windows only here and here to take holes. Looking from the top, this one may be something like this. Okay? What is the problem of this resistor? This region, please remember, this island, this resistor has used now N plus emitter region. It's very strongly doped, has got a sheet resistance around 10 ohms per square. This one. So I have metal contact here and here. This is the red region is oxide. I have metal contact here. I have adjusted the length to base ratio, which ratio such that I get the 30 ohm resistance. 10 ohms per square being the sheet resistance of this emitter, for example. Then can any one of you imagine what is the problem which I may face because of this? Any one of you? Please remember that this structure is otherwise the same as a bipolar junction transistor which I have fabricated in some other regions. Exactly the same. Only thing, I do not have proper contacts. Otherwise the structure inside has got all those layers, emitter layer, base layer, collector layer, bedded layer, everything. Beautiful transistor exists inside. Along with that resistance which I have realized, there is a very beautiful transistor, vertical junction transistor. This is called a parasitic transistor. I have realized a resistor, but along with that, unfortunately, a transistor has come as a gift of God. But this gift may not be very good gift. It may pose some problem. So what I should do to inhibit that? Any one of you? Suppose by chance this junction is forward biased and this junction is reverse biased, there will be transistor action. And lot of carriers will be injected from here and your resistance will be all disturbed. The equivalent circuit representing this resistor will be too complicated and you cannot design your circuit. I want a pure resistance of 30 ohms there. I do not want something, other components already automatically built with that. So what I should do for that? Any one of you can suggest to inhibit that. Emitter and base, you don't allow this junction to forward bias, to be forward biased. You are right, very much right. Don't allow this junction to be forward. If somehow due to any reason this junction becomes forward, you are in trouble. If you keep it floating, there is every chance. If you keep it floating like this, there is every chance that sometimes this junction will forward bias and you are in trouble. So what you do, when you are etching the window for oxide, you keep a opening here, so that your oxide looks like this now. And then you metallize like this. You just see. This is one terminal, this is the other terminal. I think you understand this. You appreciate it. If you don't do this, you are in trouble. You have to do it. So you see that it is possible in bipolar technology to realize resistance of different ranges. Whenever you are interested in realizing resistances of the order of few tens of ohms or even ohms order, you can prefer to use the emitter diffuse layer. Resistances of the order of few kilo ohms or maybe several tens of kilo ohms maximum, you prefer to use base diffusion, base layer. On the other hand, if you are interested in realizing very high resistors, quite often needed for certain leakage, etc. For example, you are planning your TTL logic. Between the base and ground, quite often we put a very high resistance. Why? To reduce the storage, to offer a leakage to the ground. And this resistance absolute value is not that important. One thing is important, it should be very high, and its TCR is not that important. So you can use the pinched base concept, which I've already pinched base concept. Base region which is pinched, P-I-N-C-H-E-D. And one can realize very high values of resistances by this technique. All these problems, which are so important, so common in bipolar ICs, that I have to make resistors. I can't get rid of it. And that is limiting my ultimate chip capability, chip size, chip complexity. All these problems can be got rid of in MOS technology, where we don't need to realize any resistance, passive resistance like this. Loads. The load resistors can be all replaced by MOSFET, another MOSFET. And that's the beauty of MOSFET, MOS Vlsi. We can realize any circuit, mostly digital of course. And today, by using MOS, people are also making linear, very good quality linear circuits also, where they are not using any resistors. Physical resistors like this, passive resistors like this, they are using, in place of that, other MOSFETs. These are called active loads, which I'll discuss in the next class, all right? Now, can you tell any one of you that in place of this kind of resistor, which is called diffuse resistors, can I use any other kind of resistors in bipolar integrated circuits? These diffuse resistors, as you can understand, there are a lot of parasitic effects. I have to know that I'll just request you to one book I'll refer for this. Glaser and Subak Sarpe. The name of the book is LSI Engineering. If you do not get the book, I think I will tell you to borrow it from me and just xerox a few pages of that book. And that gives you a lot of information. I don't have time to discuss all these things in this limited class. So I will just request you to go through it, and we may discuss some problems on it in tutorial class afterward. Okay? So I will request you to, if you first search the library, if you get the copy of the book, fine. Otherwise, one of you, the class monitor or leader, he may contact me, and I'll give the book, and he'll just quickly copy the relevant Xerox pages and return it to me. And you can make, we shall discuss some problems around that in the tutorial class. So with that, I'll just end today's discussion. Thank you.